Hello, welcome to my talk on Newton's inverting algorithm for infinite series. Another significant step for Newton to invent his calculus, or more specifically, to bring the calculus to much wider applications, as well as to solve some important problems. For instance, to allow Newton to find the series for sine and cosine functions. In this talk, I will introduce the Newton's inverting algorithm, and I will take a simple example for the Newton's inverting algorithm, and we will see why Newton chose this series to prove the correctness of his inverting algorithm. And then I will make the discussions on the Newton's inverting algorithm and the inverse series. And with the discussion, we should be able to understand the issue more clearly. Suppose we have a general power series given in a form as this, that is expressed as the power series of x. Here, the coefficient a, b, c, d alone. As we have shown based on the Newton's binomial series, the generalized binomial function can be expressed as the infinite power series, the binomial series. Of course, we may get this infinite series from other sources. Newton's inverting algorithm is proposed for seeking an inverse relation between z and x. That is, for a given infinite series, z expressed as the series of x powers, and the purpose is to find the inverse relation x expressed as the power series of z. Here we have another set of coefficients a1, b1, c1, d1, etc., which would be decided by the Newton's inverting algorithm. Newton's inverting algorithm is an important algorithm, together with the binomial series, which allows Newton to develop his calculus. For instance, the calculation of the area under a curve, to find the infinite series for sine x and cosine x. All these fantastic achievements in mathematics confirmed Newton as the co-inventor of calculus with Leibniz. Take an example below, which is a simple series Newton chose for proving his inverting algorithm. The series is z equaling to the power series of x. Next, we will follow the Newton's algorithm to find the inverse relation between z and x. Step 1. We rewrite the relation of the series as this, and name it as equation 1. So in this step, a very brutal approximation can be taken by dropping all the higher order terms of x. So we have the approximation x equaling to z. Obviously, x equaling to z is not accurate. Hence, Newton assumed an accurate solution given as x equaling to z plus p. And the purpose for the algorithm is to find what is p. So we can substitute x equaling to z plus p into equation 1. So we have the equation given as this. Now we can write the equation by ordering p. We have the expression as this. So here the bracket with p power of 0, and this bracket we have p and the p squared, p cubic, and the p power 4, etc. So this is the equation 2. And again, Newton dropped all the higher order terms of p, including p squared and higher. So we have an equation for p. Solving the equation, we have p equaling to this expression. Again, Newton made another brutal approximation by keeping only the first terms in both numerator and denominator. So we have p approximated by z squared. So we could have a better approximation for x equaling to z plus z squared. In the step 3, we can assume a beta p should be expressed as z squared plus q. And from here, we are going to find what is q. So substitute this expression into the equation 2. So we have the more complicated equation given in this. If we ordering the equation, use q powers. So we have the equation as this. This is equation 3. And again, by drop the higher order terms of q squared, and higher. So we have the equation for q as this. The solution of q is given as this. And Newton's approximation for q is taken as this. So we have a beta x expressed as z plus z squared plus z cubic. So in the step 4, we can go on to find a beta q by assuming q equaling to z cubic plus r, and we should be able to use the similar procedure to get r. Keep going the similar procedure, we should be able to find the expression for x equaling to z plus z squared plus z cubic plus z power 4, and so on. So in summary, for this inverting algorithm, for a given series as this, use the Newton's inverting algorithm, we get the inverse relation between x and z given as this. Since we know in the Newton's inverting calculation, we made a lot of brutal approximations. Thus, we may have a question: is this inverting calculation correct? For proving the correctness of the inverting calculation, we convert the series back to the binomial function. So we have the expression for z given as this. As well, we have the expression for x given as this. Obviously, this inverse relation can be obtained by solving the equation here. X should be given as another binomial function of z. So in this regard, we can see the inverting algorithm is correct. This is how Newton proved his inverting algorithm. Having talked about the correctness of Newton's inverting algorithm, but we should be careful in interpreting it. Here, I would like to make some discussions based on my personal understandings on this issue. I didn't find the relevant information in the references. The discussions here would be made on how we can interpret the inverting algorithm and the inverse series. From the simple example, the converting calculation seems perfect. We start from this series and we obtain the inverse series as this. If we convert this series back into the binomial functions, this series into this and this series into this, and we can see for the binomial functions, this and this, they can be inversible each other from this to this and from this to this. So this means these two series would be inversible each other too. If we examine the function expression, we can see that both are binomial types, and based on the Newton's binomial series, we should have the corresponding series for them. That's why we say these two series are inversible. However, when the binomial function is expanded into infinite series, there are conditions for the convergence of the series. For example, we should have limits for the first series as absolute x is smaller than 1, and the same for the second series, where the absolute z must be smaller than 1, such that these two series would be convergent. But if we examine these binomial functions, we don't have such limits if x is not equal to -1 and z is not equal to 1. However, if we want to guarantee the convergence of these two series, a limit must be applied for x as from -0.5 to 1 rather than -1 to 1, such that we can guarantee that would be within the limit. It would be from -1 to 0.5. Otherwise, the inverting algorithm might not be correct. For instance, if we take x equaling to -0.8, and we can obtain z equaling to -4.0. Obviously, in this case, the first series is convergent, but the second series is divergent. Therefore, such an inverting algorithm is not correct. Having discussed the limits of Newton's inverting algorithm, but for some series, there might not be such limits. In fact, Newton has used the inverting algorithm to obtain the infinite series for sine function. The second question on the Newton's inverting algorithm is you might not find the inverse relation for some series. For example, if we have a simple infinite series given by this, or question where we have an inverse series for this series, as I can see, there should not be an inverse series for x. The reason for this we can see. First, we can convert the series back into the binomial function, so we have the expression as this. And from this binomial function, the inverse calculation of the binomial function is given by this. So we can check. We have binomial function here, thus we have a binomial series given as this accordingly. However, the second expression here is not a binomial function. Hence, we cannot use the Newton's binomial series to get the series for this expression. That's why we don't have the inverse series for this series.